All right, let's dive in. Today, we're going to get crystal clear on 3 words we use all the time, but let's be honest, we often mix them up: speed, velocity, and acceleration. By the end of this, you will get the precise language physics uses to describe, well, pretty much everything that moves. So let's get going.
Okay, let's start with something we all know. Imagine you're on a road trip. You've just covered 50 miles, and you happen to look at the clock. It's been exactly 1 hour. So what's your speed?
Yep, easy. 50 miles per hour. It's the number you see on your dashboard, right? It feels totally intuitive. No problem there.
But hang on a second. Let me ask a slightly trickier question. Same situation. What is your velocity? It sounds like the same thing, but in the world of physics, it is definitely not.
See, to answer that question, that number, 50 miles per hour, isn't enough. You're actually missing one crucial piece of the puzzle. And that little missing piece? It's the key to understanding the entire language of motion.
So, let's learn that hidden language. Turns out, physics is really precise. It divides every single measurement of motion into one of 2 really simple but really powerful categories. And here they are: scalar and vector. A scalar is just a number, a magnitude. That's just a fancy word for how much, like 5 kilometers. But a vector has that magnitude and a direction. So you're not just talking about 5 kilometers, you're talking about 5 kilometers north. That one little addition, direction, changes everything. So keeping that in mind, let's circle back to our first term. This is the one we're all comfortable with. This is our scalar, speed. Speed, simply put, is how fast something is covering distance. That's it. It only tells you how fast. It tells you nothing about where you're going. And because there's no direction involved, it is a pure scalar quantity. And the formula? It's as easy as it gets. You just take the distance you traveled and divide it by the time it took you. So if you run 100 meters in 5 seconds, your speed is 20 meters per second. Simple as that.
Okay, you with me? Let's build on that. Now we are ready to tackle velocity. This is where we add that extra, crucial layer of information we were talking about: direction.
So, velocity is the rate that an object's position changes. But, and this is the big but, in a specific direction. The moment you say north, or up, or to the left, you're not talking about speed anymore. You're talking about velocity. And that makes it a vector. The formula looks almost the same, right? But look closely. We're using the word displacement instead of distance. Displacement isn't just how far you went, it's how far you are from your starting point, in a straight line, and in what direction. This is so important because it means you can actually change your velocity without ever changing your speed. All you have to do is turn a corner. In this table just lays it all out so perfectly. Speed, that's your scalar. Velocity, that's the vector. Does speed care about direction? Nope. But for velocity, direction is everything. And check out this last row. Speed can never, ever be negative. But velocity can. A negative velocity just means you're moving in the opposite direction from what you decided was positive. All right, now that we've got a handle on velocity, we can finally talk about the last piece of this puzzle: acceleration. And here's the connection. If velocity is about a change in position, acceleration is about a change in velocity. So, acceleration is just the rate of change of velocity. Now, this is a huge point, so listen close. It's not just about speeding up, because velocity has both speed and direction. A change in your speed or a change in your direction counts as acceleration. And since it's all about velocity, you guessed it, acceleration is a vector too. The formula for it is pretty cool. You just take your final velocity, subtract your initial velocity, and divide by how long that change took. This is also why the unit is meters per second times squared. It's a change in velocity, which is meters per second, happening over a certain amount of time, per second. Kind of neat, right?
Now, when we say acceleration, most of us think of flooring it in a car, speeding up. But what about slowing down? Well, in physics, slowing down is just negative acceleration. It even has its own names: retardation, or what we more commonly call deceleration. It's the same idea, just pushing against the direction you're moving.
So how do you actually calculate this stuff? Well, it breaks down into a really simple 3-step process. First up, step 1, figure out your starting and ending velocities. Where were you and where did you end up? Then, step 2,
You just have to know how long it took to make that change. And finally, step 3, you plug it all into that formula we just saw. Change in velocity divided by time. It's like a recipe.
Okay, quiz time. This is a classic physics question, so let's see if we can nail it. You have a car, it's turning a corner, and the speedometer is locked, rock solid at 30 miles per hour. So, is that car accelerating? What do you think?
And the answer is a big yes. It is absolutely accelerating. And this is the perfect example of why this all matters. The car's speed isn't changing, that's true. But as it turns that corner, its direction is changing every single second. And what do we know? A change in direction is a change in velocity. And any change in velocity is acceleration. Boom!
So you might be thinking, okay, scalar, vector, speed, velocity, I get it. But why does this tiny little detail about direction matter so much? Well, it matters because this precision is literally the foundation for how we describe the universe.
So let's recap the big ideas real quick. Speed is just how fast. It's a scalar. Velocity is how fast and which way. It's a vector. And acceleration? That's any change in that velocity. Speeding up, slowing down, or just turning. And believe me, this isn't just stuff for a physics test. This exact, precise language is what allows the GPS in your phone to tell you to turn left in 200 feet. It's how engineers plot the course for a rover on Mars, and it is absolutely essential to understanding the majestic orbits of the planets around the sun. Which leads us to one last little thought. We know planets are constantly turning in their orbits, which means they must be constantly accelerating. And we also know that acceleration is always caused by a force. So what's the invisible force that's always pulling on the planets, always changing their direction, and keeping them locked in that beautiful cosmic dance? Something to think about.